Hello, it's Muzhen. Welcome to today's talk and thank you all for coming. We will talk about lifelong semiconductor prediction by leveraging Kubernetes Sedana today. As we know, people now spend 80% of their time in buildings. In the meanwhile, buildings take up 40% of a city's energy consumption, the majority of which, up to 60%, comes from air conditioners. This leads us to think about whether the building air conditioner can be intelligent control in order to reduce the energy consumption and maximize occupants' thermal sensation. This paper mainly was on the semiconductor part then. Semi-comfort prediction had long been an important research topic, leveraging occupant thermal sensation, environment, and weather data, etc. To it is to train a model showing whether occupant feels cold or hot or comfort. By data-driven methods, the accuracy of thermal comfort prediction have been continuously improved, and additional devices are no longer necessary in data-driven methods. It has been widely applied for choosing building design alternatives and for the set point management of air conditioning systems. Here is also some related work. Domain studies have provided dense understanding in semiconductor research as representative in the pre- prediction of semiconductor. The research in built environment commonly study a kind of average person which were used to predict the mean response of a group of people exposed to the same environment. To achieve personalized thermal comfort, the studies in recently computer research apply various techniques from IoT. They leverage either additional devices or recurrent feedback from occupants. As thermal comfort directly is related to an individual's thermal sensation, there are also studies requesting occupants to provide feedback. To date, thermal comfort models have not been widely deployed in practice. One reason is that these models are intrusive in the sense that either extra devices needed to be installed or human feedback needed to be collected. Such intrusiveness also makes the model difficult to be portable to a large scale of buildings. Then data-driven models usually separate the data collection and the model establishment phases from the model execution phases. This can make the execution of models in practice less intrusive. Nevertheless, such a model, if was in a single task manner, needs domain experts to be familiar to different contexts in semi comfort and develop a single model to tackle all possible cases in different buildings. That is again hardly feasible in practice. And recently, multi-task learning approaches have been proposed for personalized semi comfort prediction. In these studies, efforts have been made to train different models for different contexts, and different contexts can also share their knowledge to reduce sample requirements. However, these methods focus on training and fail to consider the knowledge maintenance in an online manner. That makes it difficult to retain knowledge learned in the past and use it to help future learning. It leads to either a large number of training samples needed from before training or intensive labor to modify tasks in the long run. In this paper, the key idea is to enable online multitask semi-convert services, which we call lifelong semi-convert, and we introduce meta-knowledge, the that is the knowledge of knowledge, as talked about in the following. First, let us look at a real-world example. Real-world situation can be quite complicated because um, th- there are quite a few factors like locations and um, seasons, air conditioner strategies that can lead to model changes. Here is an example showing how a single data-driven model that infers semi-comfort in different time slots. Okay, in this example, we want to learn whether a person feel hot, comfort, or cold. This example is quite simplified um, to make things clear by assuming stable feature values. So in this example, we assume that the outdoor average temperature is 30 degrees Celsius. We see that the initial model fits well for the occupants at first. Then the targeted occupants live from outdoor to the indoor at the second time slot. Since the feature value remains the same, but the ground truth changes from hot to um, the initial model does not work anymore and has to be updated for correct prediction. But when the occupant goes outdoor at the third time slot, as we can see in the figure, the updated model is again incorrect and has to be updated again. Since the system contains only one model, it has to forget the first one and update to the second, leading to incorrect prediction when the first situation occurs again in the third time slot. This is also referred to the catastrophic forgetting. A lifelong semi-comfort system is thus needed to adapt to different time slots in numerous buildings, especially when the scenarios are usually too complicated given the limited data at the beginning. This paper, for the first time, defined a lifelong semi-comfort prediction problem. It is given historical semi-comfort tasks at past n time slots. The goal is to minimize the prediction error of the coming m plus 1 tasks. Note that the coming tasks are not necessarily in the historical task, and any elements in the previous task can be updated in the future. In fact, we encounter three major challenges to when developing such a framework. We will introduce the corresponding techniques in the following, but we are not going to dive deep into the method. Please refer to our paper for more detail if you're interested. Well, come to the techniques. How shall we make the system lifelong? Let us come back and rethink the previous example for the outdoor and indoor semi-convert prediction. It is critical to think about what is on Earth wrong in the existing system. In fact, the problem here is the lack of management knowledge of models in the single task incremental learning. Note that in this example, the system could have still worked well at time slot 3 if it can pick up and replay the first model. But the system have overwritten the knowledge of the first model, which leads to the forgetting. So when it comes to our first challenges, we will say it would be the lack of the knowledge of model. In the whole process, thermal comfort is bounded to the occupant, and the individual context usually confronted with juristic changes over time in practice. A model for each testing sample needs to be deducted and allocated when inference. It is that it is challenging to find such a proper model due to the lack of modeling knowledge in the system. Such knowledge, for example, can be the usage scope of a model. Without such knowledge, data-driven method can still suffer from either labor-intensive tuning or unstable performance in the long run after models are trained and deployed in the real-world projects. So it is important. How should we tackle this? In existing multitask learning methods, there are already task relationship discovery techniques which tackle this by using similarity measurement with historical training samples. However, in many real-world applications, training samples capture merely partial task relations. For instance, let us coming back to the example of outdoor and indoor thermocomfort prediction. The outdoor temperature serves as the feature of thermocomfort. We see that the feature value remains the same, that is always 30 degrees Celsius and the different um, comfort context. In this case, if we merely look at the sample, we may directly reduce the knowledge to the unrelated task because the feature of outdoor temperature remains the same. For example, we may use the model F1 not only in the outdoor situation but also in the indoor situation. Then we see that it can lead to performance decreasing, which is also called negative transfer in machine learning community. To fix this problem, a nature's thinking is to introduce context, which is a priori information to describe the scope of the task. For instance, the above example can be resampled into two groups with the task of location outdoor and location indoor. The location now serves as the scope of a model. To avoid negative transfer, and then we can merely transfer knowledge between tasks within similar scope. Okay. However, in real-world applications, methods with domain knowledge to develop such kind of task scope requires non-trivial human effort, bringing difficulties to the wide use of such an approach. Therefore, we wonder, okay, is there any information can be leveraged as task scope for automatic services? So our answer is yes, it's possible to leverage some source called meta-knowledge. First, the key idea in this paper is to introduce such meta-knowledge. It is the knowledge of knowledge to enable the lifelong semi-comfort. It intrinsically, the meta-knowledge is the knowledge about a model that can be used to guide the usage and maintenance of a model. For example, it can be a classifier, showing whether task model should be used for a given sample. We formally define the meta-knowledge in this paper as a mapping between the given arbitrary metadata and the performance descriptor of a model on this metadata. So-called metadata is the description information about a data set in a real-world system. It is usually designed by domain experts to daily operation of the system. That is to say, um, by connecting metadata to the performance of machine learning model, meta-knowledge can capture intrinsic domain information for task models, such as previously mentioned the location outdoor and location indoor in the previous example. Using meta-knowledge, then we are able to extract the task scope and relation with the domain knowledge automatically. It on one hand avoids negative transfer, and on the other hand can still um, work in an automatic manner to reduce human effort. So this address the first challenges by using the meta knowledge. Then confronted with the time varying data set in different building, we come across the second challenges. The meta knowledge and the models should automatically adapt to different distribution of data, metadata, without too much changes while enabling our lifelong services. It is also common to even use different machine learning models for different scenarios in some cases. Um, that is our framework that should support it. For example, common models like boosting, SVM, neural networks. Um, Due to the complexity of targeted meta-knowledge and models for various data distribution, we propose a data-driven method to extract meta-knowledge. That is the so-called meta-learning. Meta-learning refers to the learning algorithm that learns from the basic model learning algorithm. It is then a learning progress before the learning progress so that it can adapt to various basic uh, learning models. For example, it not necessarily be neural networks. Then our Leon, the proposed Leon, can be model pluggable. That is, with Leon, one can use arbitrary training models like XGBoost and SVM to establish lifelong services non-intrusively with little modification. Such a property then it can implement it with meta learning because the transfer happens on the task level instead of the parameter level. So it can adapt to different models by taking those models as black boxes. Because most existing work of lifelong learning only support neural network, using meta learning in Leon does shed some new light on lifelong learning framework development, especially when neural network is usually not the best choice for stable comfort. The proposed Leon overcomes the second challenges and adapt to buildings in 99 cities of 28 countries in 20 years between 1995 and 1995 and 2015, using the Asia Global Semi Comfort Database too. Um, Finally, it comes to the third challenges. Given limited initial samples and constantly changing context, data should be collected and the modeling knowledge needs to be updated continuously. It then remains an open question about the design of a proper maintenance strategy to continuously update models effectively and efficiently, given enormous number of possible operations of models, which is obviously a daunting job. So our proposed Leon addressed the final challenges by using online multi-task learning with unseen task detection and processing. The online multi-task learning is processed based on totally 6 operators, two, including 2 operators for meta-knowledge similarity measurement and another 4 binary operators to update meta-knowledge. Meta-knowledge base is also developed based on Brick to adapt to the task changes in different buildings. So all these components together work as our Leon framework. First, the component of meta-knowledge initialization generates the meta-knowledge given the meta-database and training samples using meta-learning. Second, with the predicted sample and the meta-knowledge space, the component of task allocation assigns a task model for the sample with meta-knowledge in the meta-knowledge space. Third, given the targeted task, the component of unseen task detection is conducted to see whether the targeted task is an unseen task. That is, those tasks can hardly be tackled properly by directly using the existing tasks in the meta-knowledge space. Finally, if the targeted task is an existing task, then the multitask prediction is conducted directly. Otherwise, when the targeted task is an unseen task, the component of unseen task processing is conducted to update the meta knowledge, including task scopes, models, samples stored in the meta knowledge space. Then we evaluate the proposed Leo method based on the uh, Asia Global Semi-Convert dataset too. The database contains buildings, as mentioned before, in 99 cities of 28 countries in 2000, in 20 years between 1995 and 2015. We also employ another 6 state-of-the-art methods as baselines. We see that on average, in terms of SMAP, the Leon method had on average over 20% of improvement over all baselines. In terms of backward transfer and forward transfer, Leon has on average an improvement up to 40%. The the backward transfer BWT here is testing the uh, method that how good the system can memorize historical task. It's basically testing um, uh, the future task model on the test set of historical samples. And the um, forward transfer metric was in an opposite way. It basically testing the uh, historical task model to on the test set of the future tasks, so it can uh, measure the ability of tackling future tasks, so-called generalization ability of the system models. Um, in all these methods and metrics, our proposed Leon shown uh, have shown the outperform performance against all these baselines. So partial code of such Leon had been released to a cloud-native edge AI platform named Kubernetes Sedona. Kubernetes extends the power of Kubernetes to the edge, and Sedona provides distributed AI templates. For example, edge cloud synergy interface like federated learning, incremental learning, and lifelong learning. Sedona enables edge cloud synergy capability to existing training and inference algorithms to reduce costs, improve model performance, and finally protect data privacy. For the time being, the overall QoS community have received over 5,100 GitHub stars, 1,400 forks, and reaches more than 10, 100,000 users and over 3,200 active communities. Kubernetes Center have obtained over 350 stars, attracting attention of nearly 400 vendors, universities, and developers, with typical applications in buildings, factories, and even satellites. The release Leonpad is the first edge cloud collaborative lifelong learning framework in industry. So that is all for today's talk, and thank you again for coming.